The first part will be from energy perspective. The second part will be from oscillatory perspective, harmonic. So, by the way, this is simple, as I said, because these three parameters, they do not depend on the amplitude. It's harmonic because this repetitive motion. So you can see that when an object is oscillating, like the spring or like this, it will oscillate back and forth. So you can see that go back and forth. The same will be with the spring. It will oscillate back and forth. Or the third system. So we will study three systems here. One, the block spring system. Two, the pendulum. And three, what we call the physical pendulum, which is anything like the grandfather clock, right? So which oscillates. This is a physical pendulum. This is another case of physical pendulum. So you can see that this go back and forth. So like a yo-yo, right? This is another case of a physical pendulum. It's anything that is not just a single mass. We also care about the rotation of the continuous distribution. So, but we studied, in the previous class, the only thing we studied was the block spring system, which is very simple if you just understand that this is the restoring force, the acceleration is just this, and this is a three formula. What will be x? You just find the derivative. And of course, the maximum will be when cosine of the angle or sine of the angle is equal to 1. Or you can use energy, and you can see from here that if you get B max is the square root of K over N A. So if you pair this EI is equally final, you can see that 1/2 cancels out and we get this formula. And this, we know that is omega squared, which is this. Omega is the square root of K over N. So we have this. So B max from energy perspective is equal to omega A, which we also found that from oscillatory perspective. Either way. All right, anyway. So if we use oscillatory perspective, this. If we use energy, this. Besides that, you need to go back to energy and remember the three theorem, which said, number one, the network is equal to the change in kinetic energy. Number two, this we will use if forces are given explicitly, just to remind you. Two, W by the non-conservative, if we have a force, non-conservative for friction, but the forces are not given, you can use also delta E, E final minus E initial. And three, if there is no non-conservative force, then EI is equally final. Depends on what you have, you will use one of the three theorems. Okay, knowing that, let's go back to the spring from energy perspective. I will start from energy perspective and then I will go over oscillatory behavior. Let's start with energy perspective. So the energy, in the first one, you just have to apply one of the theorem in the first part of the study guide. So here you have question number one. A 10 kilogram block on a horizontal frictionless surface is attached to a light spring, which force constant is given, that is K. The block is initially at rest at its equilibrium position. When a force of magnitude 80 Newton, the force is given, acting parallel to the surface, is applied to the block, as shown in the picture. What is the speed of the block when it is 13 centimeters from its equilibrium position? We want to find what will be the speed when it's 13 centimeters from the equilibrium position. All right, this is again from energy perspective. We need to solve the problem. when we are dealing with energy perspective, we need to remember one of the three theorems. In this particular case, which of the three theorems, according to the information given? The first one, immediately. So use the first one. Yes, water. So, using the first theorem, we just put W net is equal to delta K. The work done by the net force. What are the net forces acting on this one? That the work done by P, which is also a non-conservative force. We could use the second theorem as well. So the work done by P, which is equal, what is by definition the work done by P?
Force times displacement.
The force, which is P, time displacement, which is X, time cosine, in this case, what is the angle? 0 degree. So that will be equal to the change in kinetic energy. At the beginning, we don't have energy. At the end, we have energy. Plus the change, oh, by the way, there is another force here acting. The work net. So it's the work done by P plus the work. If we go by this, let me just, I prefer to use the second. I could use the first. If I know that the work done by the spring, which is opposite to the change in potential energy, opposite to the change in potential energy will be negative K over 2 x final squared minus x initial squared. You could do this, or you can say the work done by the non-conservative force, and using the second, I could use the first, is equal to delta E, which is delta K plus delta U, is the same. So the work done by the non-conservative force is just Px, which is 1/2 mv squared, that's the change in kinetic energy, plus the change in potential energy. What is the change in potential energy of the spring? At the end, when it's passing through the equilibrium position, what is the